Thank you for staying with us in the Embedded Systems Design class. And today, as promised, we will talk about the reset module and the power saving modes. So without further ado, then we will move to the first module, which is the reset module. So to reset the BIC24, there are many ways to do it. The effect of resetting the BIC24, the pointer to start the code will jump to location 0 to start the first instruction, to start the first instruction. Remember, if you go to the program memory, you will see the breakdown, and you will see at location 0, you have a go-to instruction that will move you to the beginning of your code. When you click a reset, this is exactly what will happen. Now, what are the sources that can cause a reset for you? You have the power on reset, or the POR. We have a brownout reset, which is the BOR. We have a master clear pen reset, the master clear. We have a pen specialized for that. We have the reset instruction, which is the software reset. We have a watchdog timeout reset, the watchdog timer timeout. We have the configuration mismatch, or the CM reset. It's not available in all the BIC24, only some of them. We have the trap conflict reset, which is the trap reset, illegal condition device reset, the IO PUWR. That's in case we have an illegal condition that could be an illegal opcode, an uninitialized one of the working registers, and the security also reset. So let's look at them in hardware to understand them better. We have first the power on reset. So you have a voltage source that supplies you with the VDD, usually with a certain regulator. You go and check the VDD when it rises from 0 to 1. Once it's reached a certain level, you will have this event where a flag will be risen that tells you that a power on reset event happens, and this will reset the system. That's the main reset in your BIC24. Now, as you can see, there are multiple other sources that we mentioned before, and now we will check them. Now, the reset will happen if any of them happens. So if this happens, or this happens, or this happens, or this happens, this is why we have an OR gate, followed by inversion to have an active flow system reset. And since you have an OR followed by inversion, this is actually an OR gate. Now, there is another event. It's called a brownout reset. This is in case you have a failure in the VDD, certain fluctuation, and we will see it in a timing diagram to see the difference. We have the other sources. One of them, the obvious master clear, that is active flow. We have a bin in the BIC24. If you make this bin 0, usually it's connected to a switch. This is why we have a Schmidt buffer again, but here we have the inverter. We filter out the glitches, any problems, and make sure that the edges are as sharp as possible, and then this will generate a reset for you. We also have a reset instruction. You can write down in your code a call, and you give this call specification to have an instruction in the assembly level where it will cause a reset. This is called a reset instruction. It's capital letter, as you can see here. This is the way to write it. We have also a reset that is caused by the watchdog timer. Now, this is the time where we will tell you the two different functions or jobs of the watchdog timer. The first job is the reset. So if the watchdog timer times out, expired, the rollover happens, or the timer expired, it could cause a reset. When is this happening? Only if the microcontroller is not in the sleep or the idle. So if it's not, if it is not in the sleep or the idle mode, the first job of the watchdog timer would be to reset the system. Now, what's the second job? The second job of the watchdog timer is to wake up the microcontroller from sleep or idle modes. And we will see this more in the coming few slides. But now, for now, if you enable the watchdog timer and it's ticking, and your system is not in the sleep or the idle mode, then this will cause a reset. Other than these 4 or 5 reset sources, we have the trap conflict. We also have a legal opcode. If there is an instruction that is with an opcode that is unknown. If you have a configuration mismatch, you configured one of the special function register in a conflicting matter, or you choose something unbelievable, or you make certain assumptions that made you make some mistakes in the special function registration register configurations, then this will cause the CM reset. We have the uninitialized working register. If one of the working registers for some reason is not initialized, then it will cause a reset. These are the source of resets. For these, since it has, we don't have controls over it. So if these events happen, it will reset the system. We are not gonna talk about them anymore. We will just mention them in general. For these, we will talk about them in detail. Some of them are fairly easy, like the bin. The master key is just a bin you connected to a switch, and the reset instruction is just an instruction that you write down in the software. But for the watchdog timer and the brownout and the power on reset, we will see them in detail. Now, here is a simple code that tells you the flags. And if any event happens that can cause a reset, there is a flag associated with it. Its value will change from 0 to 1. If the reset happens, based on that event, the flag will change to 1. So for each reset, you have a flag, and it's your job as a programmer. Remember the timer's flags. Whenever you have a flag, it's your job as a programmer to clear the flag after it is asserted. So this function is called a reset cause, and this is actually a simplified method from the function that was written in your book. Anyway, it says if the flag is underscore sleep, then you reset it, and you know that you are in the sleep mode. If you want to do something about this, you can write it here. If it is underscore idle, so you are in the idle mode now, similarly, this is its flag. Now notice, this will be true only if the flag is equal to 1. And it's your job as the programmer to make it 0 again. If you didn't do this, the system will be in the sleep mode forever. So make sure to reset it after it is asserted. Now, if a power on reset happens, you just plugged in the system and the VDD start to be generated. It moves quickly from 0 to 1, but once it's reached to a certain threshold, this flag will be asserted, and it's your job to make it equal to 0. And for this case, this is called the power on reset. And we will reset both flags, the power on and the brownout reset. Now, if this is the main source of a reset, this is the power on reset. There are other sources that are like in it's in a lesser rank than the power on reset. We have the software reset, which is the instruction. This is its flag. We have the watchdog timer, or the DTO. We have the external, which is this happens from the master clear. If you have a 0 in the master clear bin, remember it's an active low, then it will cause this to be asserted. When I say asserted, I mean its value is going to be equal to 1. Underscore POR, that's the brownout, and we will see it next after we explain the power on reset timing diagram. We will check the brownout reset timing diagram, and we will see the difference. We have the trap. That is, if you have a trap conflict. This is one famous problem is dividing by 0. If you have a problem like this, it will show you, it will assert this flag. And we have the IO PUWR, that's the illegal condition, if you have an illegal condition. And we have the CM for the configure mismatch. I just show you this to know the flags, and notice that here between or in the body of the F, for each one of them, it's your job to reset its value once it is asserted. Now let's check the power on reset. The power on reset ensures that the device is reset from the power on. So the VDD is 0, start going up and up and up until it reaches to its maximum VDD value. So the power on reset circuit is active until the VDD cross the VPOR threshold. We have a VPOR threshold right here, and we have another threshold called the V brownout reset, which is another threshold. Once you pass this threshold, the POR flag will be generated. So it was 0. Once you have this threshold, you are passing from 0 all the way to 1. So this is the rising edge now. Once you reach to this point, it will generate the POR. But it won't generate it directly. It will need to wait for some times, just like a safeguard time. This time is called TPOR. It will wait for this amount of time, and then it will raise the POR, or the power on reset flag. Now, why do we need this T or this time? This delay ensures the internal device circuit stability. So just as a safeguard for you. We have also another time for the brownout, but it's better to show it in the next timing diagram. So for the brownout reset, the brownout reset is generated when the VDD input falls below a certain level. So let's say you just begin your microcontroller, and now you have a power on reset. So you have POR. Now the system is running, and it was running, executing instruction, things like this. At a certain point, for some reason, there was a fluctuation in the VDD, and it goes below a certain threshold. This threshold is called the VBOR. And now you should understand why it's more than the VPOR. The VPOR is because you are actually, you know that the VDD was 0 and you are moving up. And that's why this threshold is less than the VBOR. The VBOR, the event usually is the VDD was at its normal level. It was high. It was 3.3 volt in our PIC 24. And then at a certain level, it goes down. So once it reaches to this voltage, it will tells you, oh, there is a brownout reset. The microcontroller should have this flag. So now the VDD, if it crosses this threshold, the VBOR, you wait for certain times. This time is the time for the BOR, which is like a mandatory time, plus time that you could add by software. And remember, we have in the configuration bits, when we talked last time about the configuration bits, we said that the BWRT could be specified using one of the fields of the brown out, one of the fields of the power on reset or the POR special function register. If you go check the configuration registers, or specifically the POR configuration register, you would see one of them is specifying the PWRT. And you could have time from 0 all the way to 128 milliseconds. Now, why do we need to wait for this time? It's because the fluctuation could happen many times and with different scenarios. For example, let's say this one. This is only one sync of the VDD. So if you sync for under the VBOR, and after that, after this threshold, you hit it and you went down and then you go up. At this point, you start counting for some time. This time is the TBOR plus the TPWRT. If this time expires, then it will generate a reset. It will generate a reset. Now, what else? Just so you understand what's going on here, this is the system reset, which is the active low, which we mean this one. This is the system reset that it's shown. And we are talking about the brownout, so it comes from here. When did the system reset, the active low signals happens? When the brownout or the POR flag is risen. Its value is equal to 1. So if it is 0, it means the reset is active. So when it was 1, the VDD was fine. There is no problem. The moment here it goes below the VBOR, then there is a reset. You just show that there is the brownout event happens, and you will keep at it for this specific amount of time until it expires, and then you know that there is no problem anymore, and then you go back again. The timing happens or start counting only if you go back to the value of the VDD. Notice that this scenario, what happens? 2 syncs happens. So you synced here, and then you start counting for the times, but it didn't expire. Then while you're counting, another sync happened. So now you wait for it until it goes up and you start counting again the time. And once it's gone, then the system go back to normal. For this one, you have a very long sync. So for all of this time, the flag will be asserted that there is a brownout reset even after this time, and then it goes back to normal. So in general, the brownout reset happens if the VDD falls below a certain threshold. Now let's check these events all together. It's like a scenario where you start this microcontroller. You started at the beginning, so obviously you will have a power on reset. And then after a while, you need to supply the oscillator clock for the microcontroller to start working. So what happens during that time? This is a detailed timing diagram where it shows you all the required detail. The, some of them already discussed them. The VDD goes up here, and you have two thresholds, the VPOR and the VBOR, one for the power on reset and one for the brownout reset. So in the VBOR, once at the beginning, you have a reset, obviously, since you're still not in the system is not running yet. You just started until you reach to the VPOR. After that, you have a time that you need to wait for, which is the TBPOR this time. You must wait for that. And after that, you will hit the VBOR because the brownout, the threshold for it is more than the threshold of the POR. So you will do the same. After that, since you are raising up, at this point, you will start the timing for the brownout. So you will have to wait for the TBOR plus the optional programmed time that you can wait for that you set in the configuration bits, which is the PWRT. This is the programmable power on time timer, which continues to hold the processor in the reset for a specific period of time, which is this one, after the brownout happens. And this delay ensures that the system power supplies have stabilized at the appropriate level for full speed operation. Now, after this time has elapsed, then you move from the stage of the power on and the brown out to the oscillator stage. Still, the system is not in the running mode. It's not in the running mode. You need to supply the oscillator. So what happens next? Now, for number 4 here, you need to work the oscillator. So when the this time, when the oscillator starts to give or supply its source, last time we talked about the oscillator source, and we said that there's so many of them. Once you pick one of them, whether you are using PLL or not, anyway, the oscillator output will show up at the frequency of oscillation output, and it would be supplied to both the module and the CPU of the microcontroller. At that time here, when the oscillator just started, it's not even showing up. It's a mandatory time that you need to wait for, which is the T oscillator delay. This delay is, you need to wait for it. After that, this delay is not, the oscillator is not shaping it. Once start shaping, there is another delay that's called TOST, or the timer of the oscillator. This is usually by specification. If you look at the datasheet of the BIC24, it's 1024 clock cycle, which is 2 to the power of 10. So you need to wait of this just in case, to make sure that the clock is kind of stabilized. And at this point, now it depends on your choice. If you choose PLL, if the PLL is used, then an additional T clock delay is needed to be accounted for. So that's the 3 part that you need to wait for the oscillator. A mandatory delay, before the shaping of the oscillator, another 2 to the power of 10 clock cycles to stabilize the clock. And then after that, more clock cycles that you need to wait for, which is that's if you use the field. Now at that point, you passed the power on, the brown out, and the oscillator stage. So at this point here, all what's before that, this is in the device status for it is in the reset mode. And if you check the status bit for the fail-safe monitoring, or the fail-safe check monitor, if you check that bit, you will say that it was low, meaning that there is a reset. There is a failure in the clock. Until you reach to that point, you have to wait some time, which is for the fail or for the FSCM, for the same thing here. There is a time to make sure that the fail-safe clock monitor is enabled and everything is work fine. And right after that, you are actually in the normal running mode. That's the system reset timing of all the events all together, what's going on once you start up your microcontroller. Now, again, just to revisit the configuration registers, we said that there are power on reset. It has two fields. One of them is the PWRT that we just talked about. And we explained this last time. And also we checked the oscillator, the watchdog timer, and the brown out reset. Just to remind you, for the watchdog timer, we said there are two scalars. We have a pre-scaler and a post-scaler, and we also have the windowed mode, and we have this field that make you choose whether you set or enable and disable the watchdog timer by software or always enabled by hardware. These are the two cases. And I repeated this for you just for a quick reference. So these are the details for all the fields. If you want to check the description for them, you can go back to the last video or the previous video. Now let's see the next reset. Yeah. So far we covered the power on and the brown out. We have the external reset from the master clear. It's the external reset that's generated by this pin. It's always an active low. The master clear pin is a Schmidt trigger input with an additional glitch filter. Since it's a mechanical, usually this pin is connected to a mechanical switch. The reset pulses that are longer than the minimum pulse width generates a reset. The master clear should be tied to VDD when using internal power supervisory circuit to reset the device. So if you don't choose the master clear pin, then tie it to VDD, so it will be always in normal mode unless there is other sources of reset. Usually it is tied to a push button switch, as we've told you. Now, what are the reset type that are could occur to you? What are the flags? I showed you in the code. Now it's good to know when is it set, when it is cleared, and who set that flag and who clear it. So the bits are in a special function register. All of these flags in RCON register. If you go and check the data sheet, what are the fields of the RCON, you would see all the flags that I've mentioned to you in the code. So if you take the trap flag bit, it's set by the trap. and it's cleared. Let's talk about this next time, or just when we finish this column. So each flag is set by its own event. So the trap is set by the trap conflict event. The IO power is by a legal code or the problem with the working register or a security reset. The CM, that's the configuration mismatch. The external, that's the pin of the master clear. The software, that's the reset instruction. If you have the reset instruction, it will set it or set its flag. The watchdog timer timeouts, again, that's for the watchdog timer. The sleep, the idle, it has a special instruction for each one of them. We have the power save or the PWRSAV, hashtag sleep. If you see this instruction, it will force the system to go in the sleep mode. The next one's force the system to go to idle mode. The power on reset obviously is set by the power on reset. The brown out could be by the power on or by the brown out events. These are the way you set it. Now, who clear these flags? Obviously, one thing that you always remember, if the flag is asserted, you as a programmer must reset or clear the flag. Now, if you don't, if you forgot to clear it, it will cause a lot of trouble, but just in case, know that it could be cleared by other events. And all of the reset flags could be cleared by a reset that is more powerful than them. And the only reset that's more powerful than all of them is the power on or the brown out. And this is why you see it here everywhere. Only for the watchdog timer, we said that there are two functions for them. One is the reset if the system is not in the sleep in the idle or the idle. Now, what if it is in the sleep or the idle? Then the watchdog timer function is different than the reset. It's actually waking up the processor. And that's what we will talk about next. So the watchdog timer uses either for the error recovery, it's like for debugging purposes, and that's why you do a reset. So for the error recovery, if the CPU starts a hardware operation to a peripheral and it's waiting for a response, the watchdog timer can break the CPU from waiting for a very, very long time to the point that it becomes an infinite wait loop. And it does the watchdog timer perform that by resetting the CPU. So you have a reset because of the watchdog timer for error recovery reason. The other job for the watchdog timer, as I've mentioned, is waking up the CPU from the sleep or the idle mode. If the CPU has been put in the low power mode, the clock stopped for the peripherals, partially or totally depends on the microcontroller, then the watchdog timer can be used to wake the CPU to the normal mode. That's the idea for it. To understand the watchdog timer better than that, let's check its block diagram. This is the block diagram of the watchdog timer. And one way to understand it quickly is to check the prescalers. We have two prescalers or two scalars. One of them is the watchdog timer prescaler. And we have the watchdog timer post scaler. This is a single bit. This one has 4 bits. So watchdog timer post have 4 bits. In this block diagram, as you can see, it's associated with N1, and that's associated with N2. That's different than what the N1 and the N2 of the PLL. That's a new one for only the watchdog timer. Now, the job of the prescaler is to prolong the clock cycle or the ticks that you count the watchdog timer steps by. So when you start from 0, another tick you go to 1, another tick you go to 2, and so on. To specify this tick, you have the prescaler and the post scaler to make the tick longer in case you want to wait for a longer time. Now, the two jobs of the watchdog timer. We said one job is the reset and one job is waking up the watchdog timer. When does the reset happens? It happens in case you are not in the sleep or the idle mode. If you are in the sleep and the idle mode, then this mode is equal to 1. Normal mode is identified by 0. So if you are in the normal mode, meaning that this is 0, then you will have 1 here, and then you will have a reset. If not, meaning that you are in the sleep and the idle mode, then the watchdog timer here will wake up the processor. Oh, why do we mean here? But by the outputs here, it means that this will cause the reset. It will go to us. The value will cause a reset. It will have maybe connected somewhere that it will cause the reset behavior. And this one will be connected somehow to do a wake up, generating the oscillator or making the oscillator runs in the normal mode. Now, when do you know that you have a watchdog timer timeout? You can see that you have two shift registers here. It goes like this. And here, you will have the value 1 only when the watchdog timer times out. So the selector will always see 0 unless the timeout happens. If the timeout happens, then you have a 1 here. If the watchdog timer expires, you will have 1 here. And now you will have 1 here and here because this is a demultiplexer. And based on the selection lines, either you will, or the watchdog timer wake up will be activated, or the watchdog timer reset will be activated based on this mode. That's the idea of the watchdog timer hardware. Now let's look at this part and this part. First, let's see this part. You can see that this OR is connected to the reset. So the pre and the post will be resetted, or the watchdog timer as a total will be in the reset state. It will start from 0 if these conditions or one of these conditions happen. At least one of them happens. If you have a reset from any other source, that's one reason to reset the watchdog time. If you transition to a new clock source, so you were in a frequency and then you change to another frequency, you should recount or you start again the watchdog timer. If it is enabled, it should restart again. And similarly, if you exit the sleep and the idle mode, you were in the sleep or the idle mode and the watchdog timer just woke up, then you reset again to count for the next cycle. If a power safe instruction or clear watchdog timer instructions was given, then you reset the watchdog timer. The clear watchdog timer instruction is obvious. You are giving the direction to reset the watchdog timer. The power safe instruction, if you have a power safe instruction, it's actually like you are telling the system to be forced to go to the sleep and the idle mode. So if you exit or enter the power saving mode, you need to reset the watchdog timer. Now, other than that, you can see that the other part here is connected to the clock of the watchdog timer prescaler. But this is kind of the enable circuit. when does the watchdog timer is enabled? If you have a clock moving here, going 0, 1, 0, 1, then it means that the watchdog timer beating heart is beating and it's running. And that's why you have the low power RC clock is connected here. So if this is 1 and you have a clock source, you will have a clock source generated after the AND gate. Now, who makes this 1 or 0? The circuit before that, which is the software watchdog timer enable or the F watchdog timer enable. This is the software enable and this is the hardware enable. And remember, we in the special function registers or the watchdog timer, we have a bit that enable the always enable the watchdog timer if you set this one and makes it 1, or it could be enabled or disabled if you use a software enable for the watchdog timer, which is this one. So if this is enabled or this is enabled, any of them is 1, this will be 1, and the clock will move. Now, if you choose the watchdog timer enabled to be enabled or disabled by software, this one will be 0 for sure. This one will be 0 because you choose the software. Now, in the software, if you disable, making this 0, and this is also 0, then the value here is 0. If it is 0, then whatever you are having here, it will generate 0. It's static, never change. The watchdog timer beating heart won't start. Nothing happens. That's the idea here. You see what's written here for the watchdog timer pre and the boss scaler, but we will discuss them in the next slide in a better way. The only thing that we didn't check for the watchdog timer is the window, which is this part here. First, let's check its output. Notice that the output here is connected to this AND gate. So it's equal to 1 on a watchdog timer timeout. We mean this point. And this will be 1 only if this is also 1, because this is an AND gate. So if this is 1 and there is a timeout, then it will show up in the output and the reset will happen. So what is this line connecting to? It's connected to the watchdog timer window select. This is an optional mode. You can set it up by the watchdog timer, a special function register of configuration bits. In the optional windowed mode, the watchdog timer can only be cleared in the last 25% of its timer operation, or else the processor is reset, or the microcontroller will reset. So now you have in the window mode, it's like a safeguard here, where the watchdog timer can only be cleared in the last 25% of its timer operation, or in this window. This places both minimum and maximum bounds when timing an operation, and thus provide processor reset in the case that an event requires too little time or too much time. So that's in case you activate the window mode. If you didn't activate the window mode, then this line will be always 1 and it will work normally. Notice that there is an AND gate. And here you have the clear watchdog time instruction. If you have a clear, that clear here. If you have a clear, then this clear will be asserted. The clear instruction will show that you need to do a reset if you didn't have a, a guard, a window guard, then you will have a 1 here and the reset will happen. Now let's see the how to configure the pre and the post scalars of the watchdog timer. So using a free running RC oscillator with this frequency, which is 32.768 kilohertz. So this is a low power RC oscillator frequency. The watchdog timeout occurs when the counter overflows from the maximum value, and then you reset it again to be 0. Now, what is the period? You calculate it this way. Since this is the frequency, you would say that one cycle a period is 1 over this frequency. And then you multiply it by the pre and the post scalars. Now, if you go and check the configuration bits, you would see that in the pre, the watchdog timer pre-scalar, we have only 2 options, either 32 or 128. For the post, we have certain levels. The least amount of the watchdog timer post scalar is 1, and the highest value is 32 K. So now if you want to see the upper bound and the lower bound of the watchdog timer timeout, you can plug in the least value of the pre and the post, which is 32 and 1 respectively. And you for the upper bound, you get the highest value for the pre and the post, which is the 128 for the pre and the 32K for the post. Calculating the lower bound, it's 1 millisecond. Calculating the upper bound is 128 second. So the watchdog timer, it could be anywhere from 1 millisecond all the way to 128 seconds. Again, the jobs of the watchdog timer, you have a timeout during a normal operation that will cause a reset. And you will have a timeout during sleep or idle mode that will wake up the big 24. Also, don't forget this instruction that can clear the watchdog timer. Okay, at this point, we finished the reset with its all possible scenarios. Now we will move to the power saving modes. And this is related to the watchdog timer, to just the discussion that we just finished. But we have a sleep mode. We actually have the normal mode first. There is no power saving on the normal mode. And we have the sleep mode, the idle mode, and the DOS mode. In these 3 modes, you can save the power or reduce the power consumption. In the sleep mode, the main clock is stopped to the CPU and all the peripherals. And you do that by having this instruction, which is the power save #0 or the reserved word sleep in capital letters. Now in the idle mode, and that's the difference between the sleep and idle, you have the main clock stopped to the CPU, but not the peripherals. The peripherals, all of them are working. When we say peripherals, we mean any other modules, like the UART could still receive data while you are in the idle mode. But in the sleep, all the main clock will be stopped for the CPU and all the peripherals. The key or the instruction to force the system to go to the idle mode is called power save #1, or you could use the reserved word, which is idle in capital letters. Now, before moving to the DOS, I should mention that even though in the sleep we say that the main clock is stopped in the CPU and all the peripherals, one of the peripherals is the watchdog timer. It's the watchdog timer. Now, the watchdog timer will be running even in the sleep mode. The reason is the watchdog timer is the one responsible to wake up the processor from the sleep mode. So it must be running. The clock sort or the clock should be supplied to the watchdog timer. So be aware of this. When we say all the peripherals, it's actually between double quotation because still the watchdog timer is running. Okay. For the dose mode, we've seen the oscillator block diagram. And at the end, we said that there is a dose mode specified by one of the special function registers of the oscillator, which is the oscillator control register. We have a field called dose. It has 3 bits from 0 to 2, 0, 1, 2. So you have a dose post scalar that could be associated or could be specified. It could be divided by 1, meaning that the FOC, if you divide it by 2, here you have FCY. So at this point here, we have the normal FCY, which is divided by the FOC. That's the FCY. So either you have it the same, going through 1, or divided by 2, 4, 8, 16, 32, 64, and 1, 28. How to specify the division? You specify it by assigning its dose. If you go to the special function register or simply look at this table, you could say that if your dose in decimal is 0, you have from 0 to 7, so that's 8 options specified by in binary from 0, 0, 0 to 1, 1, 1, since we have 3 bits from 0 to 2 here. Now, if the dose in the code, you write down that the dose is equal to 0, 0, 0, meaning n is equal to 1. Be aware of this. It doesn't mean that it's 0. It means it's 1. Like, for example, if you have 0, 0, 1, this is not dividing by 4. It's dividing by 16. The code for it is 0, 0, 1, but it means that the value of n that you divide by is actually 16. And the reason is, as you can see, we are actually going through power of 2 here. We are not going linearly, in a linear way from 0, 1, 2, 3. We are going power of 2. So be aware of this. Okay. In the dose mode, the main clock of the CPU is divided. It's not fully, it's divided. It could be divided by a number. This number, we call it n. We call it n. Now, how to do the current measurement of the dose if you have a dose mode scenario. Now, we say that we are saving power. We know that the power is equal to the current multiplied by the voltage. Now, our voltage is 3.3 across the board because it's a microcontroller and this is our voltage source. So if you know the current, this is kind of fixed. If you know the current, then you know the power. And this is why we say current measurement. So in the normal, sleep, and idle, and if you chose one of the doses, which is when n is equal to 2, when you see it like this, then this means n equal to 2. Now, in the normal, we have this current. In the sleep and the idle, you see the currents. In the sleep, notice that the current is very, very low. In the idle, it's kind of high compared to the sleep because the peripherals are running. And those divided by 2, kind of half of what you see here. You expect that it's going to be halved, but actually it's higher than that. Now that's for our big 24, that one that we chose, which is a big 24. That's the 32 variant of it. If we say that in normal mode, it's run at 40 megahertz. Now that's for another microcontroller. It runs at a lower speed. And that's why these numbers is actually lower than these numbers. Now, how to calculate the dose current? How to calculate the dose current? As I mentioned before we see the calculation or this equation, the power for both of these microcontroller are 3.3 volts. So to check the power consumption, simply check the current. Now, to calculate the dose current for a certain N dose mode, you have the idle current, which is this value. Should be you should be able to measure it or find its value, or in our case, if you were asked a question, then it should be given to you the idle current. And then you take the normal current and you take out the idle current from it, and that part you divide it by n. You divide it by n. Notice that the idle current should not be divided by n, because it's idle, it's always there. So you take the normal current, you take out the idle current from it, and you divide it by n. And whatever is left over, you add the idle current for it to get the total dose current. This is what I mentioned here. The idle current is kind of a base. So any dose mode current should add to this base. To understand this better, let's have an example. In this example, we have a big 24 processor that consumes 32 milliampere during normal. So that's the amount of current in the normal operation, 8 milli in the idle. So it's kind of, there is a gap in the idle mode, and only 20 nanoampere, very, very small at the sleep mode. You were asked to find what is the dose mode current if you have the FCY divided by 2. It's very important to find the value of n. Now the value of n is equal to 2. And then you just calculate based on the equation. And you calculate it this way. You say that dose current n is the idle current. The idle current, I know that it is 8 milliampere. So that's 8. And then you get the normal current minus the idle current. The normal is 32. You take out 8 from it, you end up with 32 minus 8, which is 24. And then you divide it by 2. That's 12. And then you add 8 to it, you end up with 20 milliampere. And that's the dose current in case n equal to 2. If you have, for example, n is equal to 4, you should expect lesser total current. Okay, let's have more questions. This question is for the watchdog timer manipulation, to understand the watchdog timer and how does it work. In this problem, you have a code, and you were asked to predict what will happen when the power is applied. So what will happen? You have a string, it will show up in an LCD, let's say, hello message. And then at that point, you enable the watchdog timer by software, this way. And then you went through a while loop. What will happen? If you think that you will stuck here in this while loop forever and that's it, then you are not careful enough, because you are not looking at the watchdog timer behavior. Remember, the watchdog timer jobs, 2 jobs, either reset or waking up. We are not in the idle, we are not in the sleep mode. There is no indication in the code that we are in idle or sleep mode. Because of this, the job of the watchdog timer, when it expires, it should reset the microcontroller. When we say we are resetting, it means that you will run again the main code. And from this understanding, this what will happen. The watchdog timer is enabled by software. The string hello will be displayed, and the control will remain in the infinite loop here. It would remain there until the watchdog timer expires. If it expires, then it will reset, and the main will be re-entered again. This is the behavior. Now, this code, we will do some changes to it, where now, after we enable the watchdog timer, we forced the system to go into sleep mode. When we say #0, it means we are forcing the system to go to sleep mode. So now what will happen? Now the watchdog timer will have its other job as well, which is waking up the processor. So what happens, it will go here, it will execute this instruction, and then goes to sleep mode. And it will stay in the sleep mode until the watchdog timer expires. So now from this understanding, this is what should have happened. The watchdog timer is enabled by software. The string hello will be displayed, and then the processor will be in the sleep mode. And we force it into sleep here until the watchdog timer expires. Then it will wake up, will execute its job. The watchdog timer will wake up the processor, and it will resume execution normally. It will resume right after the this instruction, which will be stuck in the while loop. Now it will stay there until the watchdog timer expires again for the next time, for the second time. And at this point, it will cause a reset, and you will re-enter the main again. So in short, the watchdog timer will do its first job here, which is the wake up. And then after it expires again inside the while, it will reset. Now, for this last example, it tells you certain specification for the normal mode, when the watchdog timer is running, and things like this. So in this problem, the frequency of oscillation is 20 megahertz. The watchdog timer period is given to you, and it's 5 seconds. Remember, we could have calculated the watchdog timer period. And I gave you the upper and lower bound in the, like maybe 5 slides ago. Now, also we have a normal current, which is 50 milliampere. The sleep count is 1 milliampere. And you were asked, what is the average current consumption? Now, you should think about any code that it might be running in normal mode, or sleep mode, or idle mode, or doze mode. These are the 4 cases of any code, either normal or sleep or idle or doze. Now, in the normal, it will consume a lot of power. If you have a doze, it will consume less. In the idle, it's even less. In the sleep, it's very little. This is the order. Now, in this code, it tells you that you have a timer that you configured, timer 2, which is 0x02. So now it's, it's prescale. It's 64. And the period register for it is this amount. And then you have its flag equal to 0. You give it here in the comment that this timer, which is timer 2, have 100 milliseconds. You could have calculated yourself. But I put it in the comments, so you don't take a lot of time calculating this. So it's 100 milliseconds. Now in the while loop, here you activated the watchdog timer. and then you went to sleep, and then you deactivated the watchdog timer. Now here you will be in the sleep mode for the amount of the watchdog time, which is given to be 5 seconds. Notice when you calculated these instructions, you were in the normal mode. And then you got stuck in the while loop forever. So the amount you are in the while is the dominant part. You could ignore anything before the while. So in the while, when you start, you were in the watchdog timer, period of time, which is the 5 seconds in the sleep mode. And then notice at this point, we didn't start the timer. We started the timer right there. And then we said, while the count is less than 10, you check this while loop, or you go through its body. If the timer expired, which is timer 2, which if it is expired, then you increase the count. You reset the flag, obviously, and then increase the count. So you here in this while, you will stay in this while for 100 milliseconds, which is the amount of time of timer 2, since you started the timer here. And notice that you started right in the statement before the while. So you have 100 milliseconds, and you will go 10 times. The iteration here is less than 10 from 0 to 9, so it's 10 times. So the amount of time for it is 1 second. Now from this reading, for the while loop, for only the while loop, you are actually in the normal mode for 1 second. And you are in the sleep mode, which is this sleep mode, for 5 seconds. Each time you go through the while, when you enter the while, you will be in the sleep for 5, and then in the normal for 1 second. 1 second, normal, 5 second sleep. Now we know the breakdown of the program. It only have a normal and sleep modes, no idle and no DOS. If there is idle and DOS, you need to account for them. Now the average current consumption is, you need also to distinguish, and you might get confused if you have so many numbers in a problem. These are the seconds, this is the time. And the numbers that were given to you here is the current, which is 5 milliampere and 1 milliampere. So we would say that you are in the normal mode, which is the 50 milliampere, 1/6. Because at both times, 5 plus 1 is equal to 6. So 1/6, which is this part, you are in the normal mode. And that's the amount of current. So 1/6 of the time, you multiply your current by 50 milliampere. And 5/6 of the time, you multiply it by 1 milliampere for the sleep. And from that, you get the average current consumption, which is 9.2 milliampere. So compare that, 9.2 milliampere. The normal is 50 milliampere. That's only 9.2 milliampere. That's the average. And the sleep is only 1 milliampere. So now you see that with this code, you actually saved some power in the microcontroller. This marks the end of this class. And at this point, we talked about the microcontroller, its CPU, data memory, program memory, and we talked about many modules, the GPIO, timer, the output compare, even the configuration bits. And we also looked at the oscillator. And today we saw the reset modes or the reset modules and even the save modes or the power saving mode. In the next lectures, we will talk about communication modules. We will talk about analog to digital and digital to analog modules. And in the next lecture, we will start by describing the external memory and how to deal with it, how to interface it, and so on. We only need an external memory if the internal memory of the microcontroller is not enough. So how to add more by interfacing the microcontroller to an external memory. And I'll see you next time.